And we'll get started for the evening. I'm just recheck again on the mic to make sure everyone can hear me.
Can hear you.
Cool. And so I see a few new names on the list from some emails I got from for new people in the club. So welcome. This is the monthly meeting for the Astronomy Fundamentals group for the Tucson Astronomy Association. Excuse me. Regular format for this meeting is there are usually two presentations. We a couple years back we finished up the 88 constellations and have moved on to a astronomer of the month topic, which tonight will be given by Stephen Ferris on astronomer Carl Sagan, and the other presentation is generally astronomy topic that's hopefully useful to those in the night sky, learning more about the night sky in general or about equipment. Trying to finish up some presentations there. And tonight, topic for that will be given by Doug Smith on a primer on dark matter. Although it's not something we as amateurs can really observe or interface with, it's still one of those important pieces in astronomy that's helpful to know about in general. Also, since one of the other agenda items I had for tonight, which we'll probably grab at the end, is to talk about whether or not we should cancel our April meeting because of the pending and total solar eclipse that same week. So I see a couple of thumbs up from some of the webcams, so I'm pretty assuming the answer to that's going to be yes. But still figure I would ask. So we'll talk about that after both presentations are over in brief. And Stephen or Doug, I don't know which one of you wants to go first. Stephen?
Steve, go first. I'll go first.
Yeah. You have co-host permission, so you can share when you're ready.
Okay, let me share screen. And hopefully I can bring this up relatively easily. It should be right here. Okay, now I need to give a warning that this is very bare bones. I kind of scratched this together the last couple nights. So if you're really looking for a in-depth study of Carl Sagan, there are, I saw mentioned a couple biographies out there, plus he wrote a number of books for the popular public, which are very good. I read a couple of them, and they would be a good place to find some information about him too. But this is a brief synopsis of Carl Sagan. It'll only take about 15, 20 minutes to go through this. And a couple things just to start out with. It's hard to pin down exactly where to place Carl Sagan in terms of his status as a scientist. He was unquestionably a scientist. The thing is, he kind of skirted the grounds between, or kind of crossed the grounds between planetary science and planetary astronomy. So he had a lot of different research interests, which didn't really pigeonhole him really easily into one category or the other, but he's mostly remembered for planetary science work at a time when, as we talked about with Gerald Kuiper, planetary science was only just becoming a separate science within astronomy at the time. So he's someone I'd probably categorize as an early planetary scientist rather than necessarily a classic astronomer. But he's best known not as a scientist, but as a popularizer. And so the thing to remember with him is that he made a number of interesting contributions to science as well, but his real talent was in communicating what science was to the public, a lot of the philosophy of the science to the public, and in some cases contributing a little bit of that philosophy as well. And so it's important to remember that he was sort of a Renaissance man among scientists for doing various things. He is not universally loved. He was certainly very popular with the public, but a lot of his fellow scientists thought he was out shamelessly self-promoting. It's probably an old debate at this point. Carl Sagan is remembered by most as being a very influential character in sort of describing science to the public. One thing I'll note is that he died fairly young. It was not completely a surprise, but he was 62, I believe, when he passed on. He was, as I'll say, to describe at the end, he came down with a rare blood disorder that ultimately resulted in pneumonia that killed him fairly young. He did suffer with that for the last couple of years of his life, and the like. So his contributions were significant, but by modern standards, he didn't live as long as some people would have hoped he would have. So a couple background things about him. He was born Carl Edward Sagan, November 9th, 1934, in Brooklyn, New York. And his parents were Rachel Molly Gruber and Samuel Sagan. His father was a Ukrainian garment worker, and his mother was a homemaker. And he described his parents as being very good people, but not necessarily the most educated or scientific people out there. But he often attributed to them sort of the sense of wonder and the hard sense of skepticism that he expressed so often in life. But he's obviously, it was a good family. There was nothing anyway unusual about it, other than the fact that his parents were coming from relatively modest backgrounds and like. His early years, he grew up in New York City, particularly in Brooklyn, at least until high school. He always had a interested in books and learning, and his parents obviously encouraged that as much as they possibly could. They kept him insulated from the details of World War II because a number of his family members were involved in the Holocaust. And he often attended the Hayden Planetarium. There's also, his parents got him chemistry sets. He was a very big science fiction fan all throughout his life, including contributing a work of science fiction, which is very well known. But he was a big fan of H.G. Wells and Edgar Rice Burroughs, which started his interest in other planets and other worlds and alien life, which were themes that became up again and again in his career as a scientist. Attended Rahway High School in Rahway, New Jersey. That was after his dad got a job in New Jersey rather than in New York City. I did not look up where Rahway is on a map. I would assume it's relatively close to New York City. I don't think the family moved very far. He was an outstanding student, but reported that he was very bored with most of his classes and didn't feel challenged by the instructors. He did comment about a couple of chemistry and science instructors who were very influential, though. He was the high school valedictorian at 16, and he attended the University of Chicago, a very, very prestigious school, but specifically because one of the few schools that would accept a 16-year-old. And that's still unusual today. There are some schools that will accept people who are underage, who are identified as prodigies and things like that. He was someone who got through high school very quickly, and they took him as a undergraduate. He works in the labs of Muller and Urey. I'll come back to Dr. Urey in a couple minutes because he did have a very big impact later on in his career after he had been established as a professor. But he graduated with a BA in 1954, which he said was a piece of cake, and then a BS in physics in 1955 from the University of Chicago, which is very well known as its physics and astronomy departments even then. Completed a master's of science also at the University of Chicago in physics in 1956 and his PhD in astronomy and astrophysics in 1960. And he worked directly with Gerard Kuiper, another person that we featured on here before, while he was still at the University of Chicago. Meaning Kuiper was still at the University of Chicago. This was before he transferred, I believe, to Texas and then back over to the University of Arizona, or to the University of Arizona. His thesis was in planetary astronomy, though, which was, as I said, an emerging field at the time within astronomy. And this is, again, sketched together information from the internet. So if you are interested, there are easily found articles which have exactly this information. It's nothing terribly creative. Early career. He received a fellowship at UC Berkeley from 1960 to 1962, typical postdoc. He did the work on the atmosphere of Venus and Mariner 2 while there. And then he was hired as an assistant professor at Harvard from 1963 to 1968. Excuse me. In 1968, he was somewhat surprisingly denied tenure at Harvard. He was an up and coming scientist, and there were several different explanations for this. One was that he was becoming a relatively public figure at this point. He certainly was not as famous as he would become, but he was becoming much more vocal about his astronomical views and attracting some attention from the public, something that the astronomy department at that point didn't think very highly of. Now, today at Harvard, a lot of astronomers write books for the popular public, and it attracts a lot of attention, so it's not terribly unusual, but then it was. The other uh, issue that came up was that his former advisor as an undergraduate wrote a letter to Harvard saying do not give him tenure, primarily because he saw him as a shameless promoter, a self-promoter. And so Harvard tenure was denied. And he was obviously very surprised by this because he was someone who, of course, was very confident in himself, but also was gaining a name for himself in a number of different fields. Another issue that came up with Sagan is he never really pigeoned himself into one area of specialty. And it was by the 60s, it was very much expected that academics would have one area of extreme area of knowledge, and Sagan was kind of bouncing between planetary science and between search for extraterrestrials and looking for origins of biology and things like that. And so he did not get tenure, but he was quickly, because he was getting a name for himself, courted by Cornell, where he worked from 1968 until his death in 1996. So even though he started out in Harvard, he really spent most of his career at Cornell, where he built up a at the time, very respectable department, and gained most of his notoriety. He was associated with NASA throughout his career. He was someone who was called into brief Apollo astronauts. Remember that he was fairly young at that point. He only got his PhD in 1960, and that was the late 60s when things were going on. He was involved with a number of planetary missions, including instrument development and experiments that were built on them. In his books, especially Cosmos, he talks a lot about his experience with the Viking programs. It's hard to clear from the book exactly what he did for Viking, but he was very involved with it. And he also created the famous golden plaques for Pioneer 10 and Pioneer 11, plus the golden records for Voyager 1 and Voyager 2. I neglected to mention this in the article, but he also was responsible for a somewhat well-known thing that many years later, where he talked to the Voyager team and convinced them before the temperatures got too cold. I believe it was either Voyager 1 or Voyager 2, and they had to turn off the cameras to take a snapshot of the Earth from the distance that the probe was at that point. Of course, I didn't know that the probe would last another 20 years. At the time, and that became the pale blue dot picture, which is, of course, the title of one of his books as well. And as we'll talk about, he was, along with his science advocacy in astronomy, also very much involved with the environmental movement. And so all of those kind of came together, of Earth being kind of that special place, but also just this tiny pale blue dot out in the universe. He was openly against both the Space Shuttle and the International Space Station because he felt they didn't produce a lot of good science, and because he felt the resources would be better spent on more planetary missions. In terms of research, he was one of the things about it is he rarely was the first person to get on these particular topics, but he was someone who would then find a particular issue, do some research on it, and then popularize it. So he was one of the first to recognize that the greenhouse effect on the atmosphere of Venus. And it's not surprising that science is collaborative, and he did collaborate on several major research things. The greenhouse effect was one of the things that he first identified and first predicted about Venus at the time. In the late 60s and early 70s. There was some hope that Venus would be a beautiful tropical paradise. And he was one of the first to say, well, not quite. He actually did some radio experiments that demonstrated the surface temperature of Venus was about 500 degrees Celsius, about 900 degrees Fahrenheit, which is roughly what we know it to be today from the modern space probes. He was one of the first to predict hydrocarbon seas on Titan and subsurface oceans on Venus. There were others who probably deserve more credit for that than he does, but he was someone who said it was at least possible. And he was directly involved with explaining the hazes on Titan as hydrocarbons after the Voyager probe, Voyager 1 in particular, discovered that the atmosphere was opaque. It was known beforehand that Titan had an atmosphere, as we talked about ages ago in a Titan presentation, but it was somewhat surprising to the Voyager team that the atmosphere was opaque, and he explained it as hazes containing hydrocarbons and organics. After, especially in the 70s, the 1970s, he was actively engaged in warning the public of dangers of human-induced climate warming. And he realized that the global warming processes that made Venus a hell planet also played out a role here. Now, remember that the greenhouse effect was certainly not discovered by Carl Sagan. That was something that had been known for several decades beforehand, as something that actually kept the Earth's atmosphere in temperature balance, so that it didn't become incredibly cold. Without a little bit of carbon dioxide, a little bit of methane, and water vapor, the temperature of this Earth's surface would be below freezing in most places. What he was concerned about was the runaway greenhouse effect, where dumping more carbon dioxide in the atmosphere would raise the temperature of the Earth, change the climate. And although he never said directly that it would lead to a runaway greenhouse on Venus, he was somewhat concerned that it would, as on Venus, he was somewhat concerned that it would lead to, actually very concerned that it would lead to major climate change. And he testified to Congress in 1985, which was decades before most people were paying attention to the global warming would change Earth's climate. He didn't get a lot of traction at that point, but it is something that he was kind of an outspoken advocate for. Other things that he was very interested in was life on other planets. He speculated about life in the atmosphere of Venus and Jupiter, even talked about creatures that would float around in airbags in Jupiter's atmosphere, heated by some crazy biological contraption, and had all sorts of speculation about that kind of thing. That, of course, is very hard to prove and probably not correct, but the atmosphere of Venus has attracted some interest of astrobiologists in the last few years because of things that plausibly could be signs of some kind of organic activity. Now, that's not to say they've discovered life, but it is interesting. He also attributed the seasonal changes of Mars to the movement of dust. And he was involved in experiments which demonstrated that amino acids could be created by basic chemicals combined with UV radiation. And he's still one of the most cited SETI and planetary scientists. And he was an advocate for the search for the extraterrestrial intelligence. It was someone who felt very deeply with that some kind of a radio search for other civilizations was a worthy scientific effort at a time when a lot of scientists thought that was bunk. Not that there were aliens out there, but that it was worth trying. And so he was very involved with that. Of course, his book, Contact, is a science fiction story based entirely on SETI. Although he was a SETI scientist, he wasn't one of the lead SETI scientists, but he was an advocate for that. He also led, along with the scientific things that he did, a very public life, especially after 1980. So his first general book for the public that was published sort of as a general read was Dragons of Eden, 1977, which sort of dealt with his beliefs and ideas on how human intelligence sort of emerged. His big breakthrough, though, was in 1980 with Cosmos. And just to go take a quick step back, Dragons of Eden actually won the Pulitzer Prize that year. But Cosmos was, at the time, something where he co-wrote and, of course, narrated the series. And, of course, everybody remembers his very droning voice and sort of melodic way of describing things. The series was the most watched in public television until 1990. And I wasn't able to find out what the one in 1990 was that replaced it. I would suspect it would be the Civil War, but I'm not sure. And then it was, unlike a lot of previous work, it was specifically targeted to a general audience because he felt that the public had lost a lot of its interest in science, and he and was becoming science illiterate. It was a topic that he, yes. Oh, okay. A topic that was a constant interest to him. It also turned him into a celebrity, and he was later parodied by Johnny Carson and several other comics, quite memorably later on. But that, of course, helped make him even more popular. And if I remember correctly, he did actually appear on like the Johnny Carson show a couple times. He was certainly not afraid of. That was a little before my time, but he was not afraid of public attention. He certainly was not in any way willing to tear down a spot on TV. Um, but most importantly, he was one of the leading science communicators of the 20th century. And it has to be remembered at that point that not a lot of scientists were doing this kind of work with the public. It's not that they didn't engage with the public, it's just the idea of a TV scientist was a little bit shaky at the time. Today, we have Neil deGrasse Tyson and the late Stephen Hawking and folks who have been very public in their advocacy for science. But in the 70s and 80s, remember he was denied tenure in part because he was becoming too much of a public character. And so it's the kind of thing where he is remembered now more as a communicator and for his scientific contribution, although his scientific contribution was not insignificant. He was focused on the importance of humanity while pointing out how small it was compared to the rest of the universe. He promoted the search for extraterrestrial intelligence, both within the scientific and the community and the public. He was a major editor for Icarus, which is the primary journal for planetary science. And he was also, because of his notoriety, at one point or another, chairperson of the Division of Planetary Sciences of the American Astronomical Association, the planetology section of the American Geophysics Union, and the astronomy section of I don't know what that stands for. I think it's the American Association of something scientists. Anyway, it was a general science organization. Um, he was a very big proponent of nuclear disarmament. In the 70s, about the time he was becoming concerned about global warming, he was doing some research on what would happen in the event of a nuclear exchange. He was not alone in that. Again, he was collaborating with other scientists who probably deserve a little bit more credit for that than he did, but he really got out the word of what a nuclear winter could potentially be. Now, to be fair, at the time, and even now, there is some who say that a nuclear winter was not as founded in the hard science as they would hope, and so meaning that basically the research wasn't as solid as some people are making it out to be. But he certainly felt that there was a major danger, and although he didn't create the term of a nuclear winter, that was Richard Turco. Was one of the people who really promoted the idea, and he co-authored the book "The Cold and the Dark: The World After Nuclear War" in 1984. And The Path Where No Man Thought, the nuclear winter and the ends of the arms race in 1990, which he advocated for with other scientists for nuclear disarmament. He had a very open argument with Edward Teller about the hypothesis. Teller, of course, had some shady reputation of his own in terms of his promotion of how to put this. He was a very strong promoter of nuclear weapons as a means of deterrence, and also to see what he could do with the physics of it. He was the father of the hydrogen bomb in a lot of ways, and was basically saying that Teller basically accused him of being a propagandist, of being an anti-nuclear advocate when it wasn't fair to do that. And even at the time, nuclear winter was considered speculative. I don't know how much further research was done on that after the Cold War, simply because the threat seemed to disappear. But my best understanding is is still not considered unlikely, if there was a nuclear exchange, that there would be some environmental impacts. Probably if it was big enough, very severe. Certainly fallout and things like that were not were something that were well documented in the explosions that happened. I think the bigger thing would have caused a global climate catastrophe. Harder to say. Contact is one of the ways that he's best known. It was a novel that was published in 1995, and he also co-wrote the film story with his then wife, third wife, Andrew Ann. And the film version, which is, I think, known among science fiction fans and astronomy fans, but not so well known outside of that, was released in 1997 after his death. So we never got to see it turn into a film. Although I believe he knew at the early stages that that was going on. Some later work that he did, Pale Blue Dot was a follow-up to Cosmos, especially the book. It was not a TV show, it was specifically a book that came out in 1995 dealing with humans in the solar system, et cetera, human futures. He wrote the foreword to Stephen Hawking's Brief History of Time. He was known for his promotion of scientific skepticism and attacks against pseudoscience. Even though he was fascinated from a very young age about the idea of aliens and extraterrestrial life, he was very much a believer that UFOs and alien abductions were a bunch of bunk. So he was one of the people who promoted the idea that it simply was not practical for in all likelihood that aliens were currently mass visiting the Earth and beaming people up and doing things to them. He did suggest after the 1991 war in Iraq that the Kuwaiti oil fires would lead to global cooling, but later admitted that prediction did not bear out. And he was also a promoter of the idea of searching for near-Earth asteroids, simply because he was he was not, again, the first, but he was a major advocate of the idea that near-Earth asteroids could potentially be a danger to the planet. A couple other things. Again, he was very involved with the idea of aliens and extraterrestrial intelligence. He felt like that he felt that his position on the Fermi paradox and the Drake equation was that Earth-like worlds and intelligent life should be common. However, as Fermi had pointed out decades earlier, no intelligent aliens had ever been detected. And he became concerned that technological civilizations would be prone to destroying themselves. And he was concerned about nuclear winter, global warming, asteroid impacts, and planetary defense. Another issue that came up with him was his position on religion, where he was very outspoken on the topic, even before Hawkins and deGrasse Tyson and other public scientists became very vocal about this. He promoted the idea that agnosticism was one of the fundamental positions of science on religion. And he openly professed a rejection of a traditional God, particularly conventions of God being an old, white, and male. And he rejected traditional spiritualism and said that scientific inquiry could provide a form of spiritual sense if understood improperly, probably. He believed in the so-called God of Spinoza, the divinity of the natural world and the natural order. In 1996, right before he died, he published a book called The Demon Haunted World. I have read that. It is excellent. If you have not read it, I recommend it. But the primary thrust was not so much about religion, but his concerns that because of the public interest in things that were not scientific, that the scientific message was getting droned out, and that we would end up in a situation where things were, the public was basically ignorant of how to think rationally. And along with another term that he's known for is the Sagan principle, which is the quote that extraordinary claims require extraordinary evidence. It actually is quoted from Cosmos, the book, not necessarily the TV series, although I think he said it in there too. It's actually based on earlier postulate by Marcello Truzzi, Theodore Flournoy in a early science fiction work, and then Laplace, 18th century scientist. And then criticisms of him include that his advocacy and public persona were seen as being self-serving and aggrandizing. Harold Urey was an early critic of his, basically saying that the guy is out to make a name for himself, and that's about it. He was criticized by some for failing to specialize in any one area. He had a lot of different interests and never really established himself as an expert in any one of them. And those two factors may have cost him his Harvard tenure. And his views on nuclear winter have been criticized as being inadequately robust, meaning that the science wasn't strong enough at the time to support that particular position. In his private life, he was married 3 times. Lynn Margulies, who's a very known biologist, well-known biologist, Linda Salzman and Andrew Ann. And his 5 children are Jeremy, Dorian, Nick, Alexandra, and Samuel. And he I had a very hard time pronouncing this, myelodysplasia in 1994. And if you know it better than I do, I apologize for ruining that word. And he died as a complication of the disease in December 20th, 1996, at the age of, I believe, 62. He's buried at Lakeview Cemetery, Ithaca, New York. So overall, a very public, very famous life. As I said before, his scientific contributions were notable but not critical. But his contributions in expanding the public awareness of science and the scientific method was crucial at a time when he felt very deeply that scientific literacy and understanding of the scientific process were waning in the public. Certainly, there's reasons to think that that was the case, but I don't want to go there tonight. Let's just say that I think that his ability to communicate science and his ability to get the public interested in astronomy. A lot of us may have. I was too young to be a cosmos person, but I know a lot of people got into astronomy because of that series and because of his books and the like. And so, certainly a very important communicator in getting the message out of what astronomy is all about and space sciences and a lot of different topics. So, any questions? All right. I guess we're good.
Thank you very
Hey,
much, Stephen.
Stephen, very good presentation. You did more than scratch the surface, I think, especially talking about that. I'm a little bit older than you. I remember a lot of those interviews you did with Carson, and I suspect, and this is just my opinion, my belief, because one of the things a lot of this not liking him not getting tenure, this all occurred in the 1960s when astronomy was still very much old school and, as they say, a good old boy network, which existed in a lot of arenas, a lot of disciplines. And I suspect he was a little bit different than a lot of his colleagues. And I think that's what actually cost him tenure. I wasn't aware of the promotions he was doing in the mid 60s. They came more or less in the late 60s, early 70s.
And
And by
that's I was
Go
going to say
ahead.
that's the funny thing about it is he was not that big of a character yet, and so I don't know what you're. I believe was a chemist, not an astronomer, but it is or a biochemist.
Yeah,
But
he
it's the
was,
kind of
yeah.
thing where the point being, he hadn't even started yet compared to what he would become, and they were already having a fit with it. So it's like that. That was really surprising.
And I
That
can
even
remember
this,
some of those early interviews. He would speak about the science. Now, granted, he may have said things, or maybe he held, certain tenets that may have rubbed, they didn't seem inordinate, though. He wasn't a wild man, but he never spoke about himself. He spoke about the science. So that's why self-promoting, well, I guess when he started writing the books, yeah, when the books came out and they would talk about, of course, anybody would do that. But to me, that was the only self-promotion that really
yeah,
went on. And it was more so, he wanted to talk about the contents of those
yeah,
books and
yeah,
things like that, not so much
yeah,
the fact that he wrote them. So I think some of that, you know, bad feeling was a little bit misplaced, and I think a lot of it is owed to, it's just like how women were treated in a lot of
yeah,
disciplines, even in astronomy in the 60s. They weren't
yeah,
recognized. They had been doing some good work and still had yet to be
yeah,
recognized. I
yeah.
suspect there was some of that, very
And
similar going on.
And as I said, a lot of the scientists felt they were too good to communicate in the way that he did with the public. And so he got into a little bit of trouble with sort of being willing to be a public character at a time when scientists was very much, especially in astronomy, sort of, as you say, a good old boys club. Go
Yeah, he
ahead.
was one of the first scientists to actually come out and try to promote a science. I mean, the only
Yeah.
other one I was familiar with, and he was more so a naturalist, was Attenborough, and that was about it. You didn't see this in the popular or mainstream media, I guess.
Yeah.
So, thank
Doug, were
you.
you going to say something?
No, my
Okay.
Zoom is crashing.
Okay. and the thing is that as I said, he's remembered as probably the first really big public persona of astronomy. And as I said, today we have a lot of those. But before then, it was kind of a tweedy field that people did on mountaintops and at Harvard Observatory and things like that. And he very much went out and promoted things. There were a couple things that were controversial that I didn't mention in there, one of which was his advocacy for marijuana use. He was very open about smoking weed at a time when certain elements of the public were not terribly thrilled about that. Certain elements of the public thought it was great, but it did create a little bit of controversy in terms of being somewhat open about his own use of drugs. He never admitted to going anywhere beyond marijuana, but it was something where that raised a few eyebrows in the scientific community. Now, I very much doubt in the 60s there were, I'm sure there were plenty of other people in these departments who were doing the same thing, but at the same time, you didn't talk about that kind of stuff if you were coming from Harvard or Cornell. And so that was something where he was a little bit also realized that in the 70s and 80s, nuclear disarmament was a very controversial concept because there were a lot of folks who felt that to speak out against, the military was not a good thing. And he was very open, not so much about, any particular wars or anything, but the nuclear war was a major danger to human civilization and survival. And that didn't necessarily go over well with everybody. But I think that the thing that has to remember with him is that, he was on PBS. He was talking to Johnny Carson. He was going on TV shows. I was joking with some friend, maybe he went on Sesame Street. I doubt that very much, but that's the kind of thing he would do. And so because of that, he attracted some negative attention from other astronomers who felt that was not appropriate. Today, I don't think anyone would have a question, and it's become very common. He did also, I want to say this, having known some of these people, launch a new breed of scientists who were much more open in their public advocacy and have done amazing jobs at trying to communicate science to the general public in ways that probably didn't happen 50 or 60 years ago. And I think that is a major thing to this day of the astronomy outreach owes an enormous amount to what he did. And that would be, I think, is probably his biggest contribution.
I think you're spot on there, and that's exactly what it is. And it's, even to a certain extent, what we do in this club so much.
Yeah.
It's one thing to be a club of amateur astronomers, but I think it says something when you go out there and work with the public or try to share and provide. Just like that's essentially that's the way I viewed what he was doing, and what subsequently, I think he was a little bit of a trailblazer. You look at all the folks that have come out now that have written books trying to speak not just to their colleagues, but more importantly to the everyday man. Some of physicists like Green and a few others that have written books, and other astronomers, and it's really kind of fascinating to read some of this stuff because they're not speaking to other astronomers; they're speaking or trying to speak to the general public. And I think some of them do a real good job at it. And I think in part and parcel, they have a lot to thank him, to thank Sagan for and being able to do that.
And before I sign off, I do make one major disclaimer. Almost all that came from Wikipedia. So that was the one thing I was a little concerned about. I did not have time to just consult a lot of other sources. So that was the one thing. But I am familiar enough with this life to know that it was pretty much accurate information. It was just not necessarily as broad as it could be. So I apologize for that.
Thanks, Stephen. Doug, I've seen you bounce around a couple of times. Your computer situation stable?
No, I don't think it is.
You want to give it a shot anyway?
I'll give it a shot, but I think I'm probably going to end up maybe just sending you the presentation and letting you do it as best you can.
Okay.
But I'll give it a shot, but it's not holding up.
Oh, I need to make you.
By the way, Steve, I had the pleasure of meeting Carl Sagan once. When I was in graduate school in 1978 at SUNY Stony Brook, one of the professors there, Dr. Tobias Owen, was on the Voyager imaging team, and Carl Sagan paid a visit to the university during the Voyager flyby of Jupiter when they made the discovery of the rings. So I had a chance to meet the guy.
He was
Very
supposedly
cool.
a very charismatic person, a little bit of a pompous ass, but
He was an interesting person.
he was a
He
very
gave, he
charismatic
gave
man.
he gave a quick little 15-minute lecture to the astronomy students in the lecture hall, and he hung out at Toby Owen's office for the better part of the day, and then he flew on back to Pasadena. So, all right, let me see if I can do this. Just hope it holds up. Oh boy, come on.
Screen share still coming through.
What's it doing? Jeez, really?
I can see PowerPoint.
All right, it's up. You know, all this nonsense. Okay, so as Connor said, I'm going to give a primer on dark matter. If my Zoom holds up. Okay, and I always have a humorous slide at the front of my presentation. Okay, so dark matter is a really interesting topic. I found no end of material. It's obviously one of the most important topics in modern astronomy today. It's one of the hot topics of research. I was surprised to learn that there were proposals about dark matter as far back as the middle of the 19th century. It should be noted, though, that most of these early theories and presentations about dark matter back then were based on erroneous data, and the concept of dark matter was not taken seriously by astronomers until the 20th century, middle of the 20th century. So I'm going to go through kind of the history of how it got discovered and who discovered it and so on. And I'm going to leave out all the mathematics because it's extremely complex and involved. But I'll go through it as best I can. Surprisingly enough, the first known hypothesis that I could find for the existence of dark matter was put forward by Lord Kelvin. You remember him. He's the guy who invented the Kelvin temperature scale. In 1884, he published an article in a book called The Baltimore Lectures on Molecular Dynamics and the Wave Theory of Light. It's quite a title. And he had studied the dispersion relation of the velocities of all the nearby stars. And using statistical analysis, he concluded that there must be many, many, many stars that are dark, basically, that we can't see. He based that on a statistical analysis of the velocities of the nearby stars. Turns out that was completely wrong analysis, but right conclusion, wrong proof. 1906, our friend Poincaré, you've all heard that name before, Henry Poincaré, famous mathematician. He published an article called The Milky Way and Theory of Gases. And in that publication, he coined the phrase dark matter, in French, matière obscure, by discussing Kelvin's work. and he found that the amount of dark matter would need to be less than that of the visible matter. We know that's wrong, but again, they at least were coming up with something.
One other thing that I had always kind of linked about with dark matter in the early days was that it was derived from the concept that was then known as aether, which was this hypothetical substance in the universe that light traveled through, and it's what allowed light to be transmitted.
That's partly true, but these two gentlemen were not talking about the ether in the sense. They were both suggesting that there were, in the case of Kelvin, he was suggesting that there were many millions of stars out there that were dark stars. So he wasn't talking about ether in the sense of the ether. I know what you're talking about, Connor. He was talking about actual stars, black stars, dark stars.
I get what you're saying. I was just adding in some additional historic context that even before these gentlemen, there was a similar thing going around, and these are just further refinements and more, probably the first, to your point, concrete verbalization of what we now know as dark matter.
Yeah. Now, as I pointed out, both of these men's computations were very erroneous and were based on bad concepts to begin with. But you have to remember that both of this work is long before Hubble had even discovered that the Milky Way was a separate galaxy and that the other galaxies like Andromeda and so on were outside the Milky Way. This is even before that. So at this time, astronomers thought everything was in the Milky Way, so to speak. And the Andromeda galaxy was actually called the Andromeda Nebula, and so on. And the spectroscopes that were being used at this time, while they were certainly probably the best spectroscopes that could be built for that time, they would be considered primitive by today's standards. So that's something to think about, that these men were able to do what they at least come up with something. 1932. Now, by now, Hubble has published his work, and we now realize, the astronomers now realize that Andromeda and other galaxies are extra Milky Way galaxies per se, and so the universe has changed. You finally got a decent work here. The Dutch astronomer Jan Oort, of the Oort cloud fame, he hypothesized the existence of dark matter in 1932. What Oort did was he was studying the stellar motions in the local galactic neighborhood, in our own Milky Way still, and it came to the conclusion that the mass in the galactic plane must be considerably greater than what you could see. And again, this turned out to be an erroneous calculation, but it's an interesting one. And when you think about it, all these people, and there were others in here, but these are the three main ones that did it at this time. They're doing these calculations, they're making these presentations, they're saying that there's dark matter, but the astronomy community as a whole is basically ignoring them because they quickly find that there's errors in the computations and that they're based on bad assumptions, and so the work is getting thrown out, not taken seriously. So nobody's paying attention to anything yet. It's being blown off until you get to Zwicky. 1933, Franz Zwicky. Did I pronounce that name? Fritz Zwicky. He started looking at galaxy clusters when he was working at Caltech. And he came to the same conclusion, that there must be a lot of dark stuff out there. What he did was he looked at the Coma, specifically, he looked at the Coma cluster, which is in that picture at the bottom right, of galaxies. And he applied what's called the virial theory to it. For those of you who don't know what statistical mechanics, this is the one place where I'll give a little talk about a little mathematics. The virial theorem is a theorem in statistical mechanics. It's widely used in, what is it? thermodynamics. It's a theory that relates kinetic energy, total kinetic energy, total potential energy of a system, a stable, closed system of discrete particles that are bound together by some kind of conservative force, okay? And in particular, the virial theorem takes on a very specific form that can be solved, that has a specific solution, if the force is of the form r raised to the power n. Now, gravity is, of course, a conservative force because it's of the form 1 over r squared, r to the minus 2, if you like. So it falls into that category very nicely. So what Zwicky did was he applied the virial theorem to the coma cluster. He treated the coma cluster of galaxies as a closed system of discrete particles, and he applied the virial theorem to it to measure all the velocities and all the other information, the kinetic energy, potential energy, all the stuff about all the members of the galactic cluster. And based on his work, he estimated that the cluster must contain about 400 times more mass than you could see. Now, that turns out to be a wrong number by a factor of 10. He came up with the wrong number basically because he was using an inaccurate number for the Hubble constant, which figures into that whole calculation. But his method was right on the nose. And if you do the same calculation today on the coma cluster using the virial theorem and his methodology, you would come up with a pretty accurate number that about 90% of the mass of the coma cluster is dark. So Zwicky did it right. Just used the wrong number for the Hubble constant. Okay, virial theorem, yeah. Horace Babcock. Now, we're getting a little later, 1939. He starts looking at rotation curve. Specifically, he looked at the rotation curve for the Andromeda Galaxy, okay? And he very quickly realized that there was something very wrong with the rotation curve, that the stars on the outside edge of the galaxy were moving way too fast. And he came up that there was a mass to luminosity ratio increased radially. That is, the farther away you got from the center of the galaxy, the more mass there was, which obviously seemed totally counterintuitive. When you look at the galaxy, you think all the mass is in the middle and the amount of mass falls off that you go out. He came up with the relationship that it actually increased as you moved farther away from the center of the galaxy. Now, he attributed it incorrectly to light absorption within the galaxy, or, quote, modified dynamics, and not to the missing mass or dark matter. But what he did, importantly, was he pointed out the problem with the rotation curve of the galaxy. There's something wrong with the way the stuff in the galaxy is moving. The following year, 1940, Jan Oort, our friend Oort again, wrote a similar paper about NGC 3115, which is another large edge-on galaxy. And he looked at the rotation curve as a function of radial distance from the center and came up with a similar conclusion. That's an interesting picture of Babcock, I found. He's actually working at the Coude focus on the 200-inch Mount Palomar scope there. That's an interesting photograph. So here's what the problem is, what we're seeing in rotation curves. If you look at a spiral galaxy, okay, and you assume that the only mass in the galaxy is what you see visually, the stars, as you move farther away from the center of the galaxy, their rotation speed around the center of the galaxy should fall off as a function of 1 over r. I mean, if you think about the planets rotating around the sun, the farther away you get from the sun, the slower the planets are going. And it's a 1/r function, Kepler's laws, okay? And that's not what you see when you look at galaxies' rotation curves. If you, in this picture here, that dashed line on the bottom is your standard Kepler velocity curve for a typical spiral galaxy if the mass was distributed only based on what you saw visually. This is what you'd expect to see in terms of the rotation speed of the stars going around the galaxy. It would be that line there. It falls off as 1/r. Okay. Instead, what they measured for the galaxies, specifically Andromeda and that other NGC galaxy that Oort looked at, was that curve on the top, which is very flat, which doesn't make any sense unless you do something to make it flat. The other problem you have with spiral galaxies is the fact that they are spiral galaxies. If you only had Keplerian rotation of the matter in the galaxy, the spiral structure would get ripped apart very fast because you have the differential rotation between the outside of the galaxy and the inside of the galaxy. The spiral structures wouldn't last very long. They'd be gone within a couple of rotations. They'd be completely dissipated. But that's not what we're observing. It's in most galaxies, you're looking at galaxies where it's very obvious that the spiral structure is very persistent and has probably been there for billions of years, if not longer. And there's no way to explain that unless you have basically little or no differential rotation so that the spiral structure is maintained as the galaxy rotates. So that was the other problem with rotation curves that people were noticing. So this problem sat around for a long time. Professional astronomers are stubborn. They don't like to accept things that don't make sense logically. And at the time, the concept of dark matter was just something nobody wanted to accept. They tried all kinds of other ways to explain the rotation curve issue and the spiral structure issue. They came up with a number of different theories to try to get around the idea of dark matter. They didn't want to have dark matter. Dark matter was evil. You didn't want to have dark matter.
Well, in their defense, a lot of astronomers still hate dark matter
I know.
for these very reasons.
A lot of astronomers still hate dark matter. That's true. But boy, they really hated it back in the 60s and the 70s. The evidence just kept coming in now. You had Seth Shostak in the 1960s. He was doing radio astronomy work. And he looked at a half a dozen different galaxies and found the same thing. Their outer edges are spinning way too fast. This evidence just kept piling up. More and more observations just kept coming in. You'd get more sensitive telescopes, more sensitive radio telescopes, more sensitive spectroscopes and everything else. And it just added to the pile of evidence. These three people, Rubin, Freeman, and what's his last name? Kent. William Kent. I can't. Ford. Did a lot of work in the 60s and the 70s which provided a lot more strong evidence. Rubin and Ford put together a new spectrograph, which was many, many times more sensitive than any spectrograph that had been used before. And they were to do a lot of measurements, again, on galaxy rotation curves. And they put together a very important paper in 1980, which I looked up and read, and it's quite an impressive paper. It goes through and does everything for the galaxies that they looked at, and then even provides a mass distribution showing how the mass density increases as you radially move away from the center of the galaxy and everything. And it was a very important paper. That's considered one of the key papers of dark matter discovery. And again, they came up with the same conclusion that most galaxies contain between 5 and 6 times as much dark stuff as visible stuff. Finally, by around 1980, I would say, astronomers were beginning to accept the need, you might say, for dark matter to stabilize the galaxy's rotation curves and everything. And it actually then, at that point, became a problem in astronomy in the sense that no longer were they astronomers talking about, do we have to have dark matter? They started talking about, well, what is dark matter? So they had kind of accepted, okay, the stuff exists. Now, what is it? So that kind of happened around 1980-ish. It's when they started that thinking. An example of one of the theories that was used to try to explain away dark matter and to try to explain some of the issues with spiral galaxies was something called density wave theory. This was something that came out. I remember this came out in, I remember seeing the articles about this in Scientific American and some other journals that popped out in the 70s and in the 60s, where they said, well, you don't need to have dark matter to have stable spiral structures in galaxies. You could have what they call density waves. And so if you look at this figure carefully, each of those particles is in an elliptical orbit around the center of the galaxy. But because of the way the relation of those ellipses are evenly distributed like that, you end up with these two spiral arms that are nothing more than density waves, actually. And they're stable. Okay. So this concept was not totally off the mark, although it doesn't explain the rotation velocities at all. It only partly explains the possibility of stable structures in a spiral galaxy. Turns out this is not how spiral arms form, and this is not what keeps spiral arms in place. But it was an interesting idea. And like I said, this was initially proposed as a way around dark matter. Of course, it isn't. Now, it turns out this theory is still used today because the theory is very valid and works very well at predicting some of the features in planetary rings, like Saturn's rings and Jupiter's rings. A lot of the features that are visible can be explained by density wave issues within the ring particles. So it is an interesting theory. But again, it was just a way to try to sidestep dark matter. At the time that Rubin and Ford were doing their work, you had other people, the radio astronomers were starting to use some of the larger instruments. You had a brand new 300-foot radio telescope that had been built at Green Bank in West Virginia, and there was a nice 250 radio dish that had just been constructed at Jodrell Bank in England, and both these dishes were utilized to map the 21 centimeter line in nearby galaxies. They found that the radial distribution of the atomic hydrogen extends way beyond what you can see visually for a galaxy, and therefore they can measure rotation curves much farther out away from the center of the galaxy than just looking at the visual components. And so they were able to expand on their measurements of the rotation curves of nearby galaxies. And just as in the visual measurements using spectroscopes, the same thing with the radio measurements of the hydrogen regions did not follow Keplerian curves. It stayed flatline. So for example, here's some work that was done. Roberts and Whitehurst was able to trace the rotational velocity of Andromeda out to a distance of 30 kiloparsecs, which is way beyond the edge of the visual galaxy. And a couple other guys, Rockstead and Chalstek, published hydrogen rotation curves of 5 different spirals using the Owens Valley radial telescopes. And as you can see in these 2 pictures, the picture on the right is the rotation curve for M33. And you can see with the radio observations in 21 centimeters, it just continues being flat, just keeps going flat line, farther and farther out. And then if you look at the 5 galaxies on the left, they're all pretty flat line too. And you've got the Milky Ways in there, and it's pretty flat line, really. These little wiggles there, but it's basically a flat line. So basically every spiral galaxy has this kind of a rotation curve. And then, as I said, you started getting other types of observations, which also supported dark matter. In the 1980s, you started getting gravitational lensing measurements of background objects. You'd look at galaxy clusters, and you can, by looking at the gravitational lensing, you can compute how much mass there is in the galaxy cluster that's causing the lensing. And you can look at temperature distribution of galaxies and clusters. They started looking at the pattern of non-uniformities in the background, microwave background. And all of these measurements started coming up that you've got a lot of dark matter out there, and it's roughly 80 to 85% of the mass of the universe is dark stuff that you can't see. So just, again, a summary of the kind of evidence that they've got to support dark matter being there. Obviously, the big one is the galactic rotation curves. That was the obvious one. The spiral structure persistence. Spiral arms don't seem to dissipate. Although we obviously haven't looked at spiral galaxies for a long enough period to see if they dissipate or not over time, but you can do a statistical analysis and say, well, if they dissipated after just a couple rotations, how many spiral galaxies would we still see that still had spiral structures? You wouldn't see very many. Velocity dispersions, you can actually do that kind of analysis using the virial theorem, and you can come up with the correct results. If you do that kind of work, you will get answers that imply there's a lot more mass in the closed system than you think there is. Galaxy clusters, like we did on the Coma cluster and other clusters, you can look at the galaxy clusters, and there's a lot of different ways to measure the mass of a galaxy cluster. Every time you do it, you come up with the same answer. The amount of dark stuff is about 5 times as much as the light stuff. Gravitational lensing. This is another way of looking at galaxy clusters. In this case, there was one case that I found where they actually looked at a galaxy cluster and they were able to map the dark matter distribution for this particular galaxy cluster. That's the cluster, MAX J0416, blah, 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 blah. And they were able to map it. The cosmic microwave background, there are non-uniformities in the microwave background that have been mapped very carefully. And all of the mathematics and analysis that they do and the assumptions they do about the Big Bang and the expansion of the universe and all that comes up with the idea that a lot of these, quote, non-uniformities must be due to there must be a certain amount of dark matter, and there are limits on it. It's got to be above this limit or below this limit kind of thing. They put limits on it.
So real quick before we move off from this slide,
Sure.
does anybody not know what gravitational lensing and the cosmic microwave background are? Because it's kind of important to help
Sorry.
to help understand some of this.
Okay, I'm not hearing
and
any.
I'm not either, so I'm going to assume that
Okay.
there is some understanding of what those two concepts are, because they're very important in modern astronomy, professional astronomy today, not so much for amateur, but
And this is an interesting one that I had never heard of before, but I found this. There's a cluster of galaxies that are colliding with each other. It's called the bullet cluster. And apparently there are certain properties of this colliding cluster of galaxies that could only be explained in one of two ways. Either there's a lot of dark matter distributed in a certain way around these two clusters, or there's a serious problem with general relativity. Okay, there's something very wrong with this particular colliding galaxy that could not be explained. If you assume that dark matter did not exist, then you would have to make major changes to general relativity. So that's an interesting one too. And then of course there are the whole list of other things that were done to show that there's dark matter. These are just the major ones that I found. So, and then there's always the question, well, what is dark matter? Well, the short answer, we don't know. It has a technical definition. It's a form of matter that only interacts with baryonic matter through gravity. Okay, that's the only way it interacts with baryonic matter. Baryonic matter is all your normal matter, protons, neutrons, electrons, and other subatomic particles and so on. And dark matter only interacts with that type of matter through gravity. Now, there is a possibility that some of, quote, the dark matter is made up of ordinary baryonic matter in the form of black holes, black dwarf stars, and etc. However, there is lots of strong evidence that this must be a very small component. Like less than 2%, I think, is the number I saw. And this type of matter, we have ways to detect this stuff if it's out there. So since we haven't detected much of it, that's not a major component. It's pretty much ignored when cosmologists talk about black matter or dark matter. They're ignoring these things. These are considered something else, normal stuff that just happens in the regular evolution of stars and things. Currently, the leading candidate for what they think the majority of dark matter is what's called primordial black holes, which is interesting. And what that is basically is they think that in the very early stages of the universe, shortly after the Big Bang occurred, there was a lot of subatomic stuff floating around, and in the very early universe, it got condensed into gravitationally collapsed black holes. Okay, and they think that there's a lot of this stuff floating around in the form of primordial black holes. They think that's the primary component. That's just a theory, like any other theory. There's no proof for it. They have limits on, there are limits on how big these primordial black holes can be and how small they can be. If they're too small, then they dissipate according to Hawking radiation. They literally disappear. And if they're too big, then there's other problems associated with them. I don't know the exact numbers. I think the small number on the small side, 10 to the 11th kilograms, I think is the number I saw for the limit on the small size. I don't remember what the limit on the large size is. 10 to 11 kilograms is pretty small in terms of scale of stars and stuff, right? That's not very big, is it? I don't think it is. But anyway, that's what I read in the papers that I looked at. They think the leading candidate for the majority of dark matter is in the form of what they call primordial black holes. Okay. Now, they've actually gone and mapped the distribution of dark matter around the Milky Way. And this picture on the right sort of shows how it's distributed. There is a large halo of dark matter that's more or less homogeneous. But within that halo, there are these, what they call subhalos, areas of concentrated dark matter, if you like, kind of balls of more concentrated stuff. And they think that this halo is, the scale here is not correct. The halo, they figure, could extend 3 to 5 times the actual radius of the visual component of the Milky Way. So it goes way out pretty deep. So this would be like
real quick, Doug.
Go ahead, ask.
To chime in on so 10 to the 11th kilograms is roughly 1/1000th the mass of the Earth. So
yeah, so it's pretty small. But it's not any smaller than that, though, and they would dissipate from Hawking radiation. They would have evaporated, so to speak. So that there is a lower limit, but like I said, I don't know what the upper limit is. And this, my last slide, this is an artist's impression of what the Milky Way would look like if you could see the dark matter. All of that blue stuff around this galaxy in the middle there, that would be your dark matter. And it's got a filamentary kind of structure with clumpiness in it. And where the filaments intersect are those what they call subhalo regions. And this is sort of what you might see if you could actually visually see the dark matter. It's what they think it looks like. So, and that's what I've got. And my Zoom held up. I'm surprised.
Well done, Doug.
thank you, Doug.
I'm going to get to repeat the same talk to the people down in Green Valley.
Any questions for Doug or in general?
Hey, Doug, I do have one question. I know your presentation was primarily about dark matter, but
Yeah.
how do you equate that to dark energy? My understanding was, and I'm just looking for the real high level. My understanding was when you look at all these things, what we can see, and then dark energy. The dark energy is about 60 to 65%. Dark matter about another 20 to 25, maybe 30. Then the stuff we can see is a very small portion of what we think is actually out there. Is that about right?
No.
Okay.
I don't like to put the two together. And I made this point to the group in Green Valley. I gave a talk a few months ago to the Green Valley people. They asked me the same question. Keep in mind, dark matter is mass.
Right.
It's actually something that's there. Dark energy is not mass. It's energy. Okay. And the guy gave a nice talk at the TAAA general meeting some months back. He talked about the dark energy and it's a repulsive force is what it is. Okay. And one theory for dark energy is that it's a additive force. You know, if you think of your regular gravity force, Newton's, F equals gmm over r squared, you add a plus sign to the end of that with with a constant multiplied by r, and the constant's on the order of 10 to the minus 46, so it's very small, but over large distances, it adds up to something. And so it's not mass. But if you think in terms of the total mass energy of the universe,
Yes.
then your numbers are not too far off.
Okay. I mean, that's what I've seen in the popular literature, but
Yeah.
and I know that this
It's
is
really important to make the distinction that dark matter is matter, it's mass.
right.
It has gravity. Dark energy is not mass. It does not have gravity. It's a repulsive force
Right.
of some kind.
A lot of times you see it talk in the same breath. And so and I understand the difference, energy, mass, two different things, but
gotta keep them apart.
yeah. Okay, thank you.
So another question.
Go ahead.
Go.
You just before this slide, perhaps, you mentioned that the vast majority of dark matter, the leading candidate is that the majority of dark matter is made up of
primordial black holes.
Right. So my question
Current
is kind
theory.
Beg your pardon?
That's the current theory.
Okay. So I guess my question is before that. You defined what primordial black holes are.
Yes.
Is there any other kind of black hole other than primordial black holes? Is it possible that black holes have actually developed with the aging of the universe?
Well, of course, we have all the regular black holes that we know about in standard astronomy, from a stellar collapse, from a star that goes supernova, you get a black hole, or we have all the standard black holes. We have the supermassive black holes that are at the center of most galaxies, including the Milky Way. These are the standard black holes that we can detect by X-ray emission and a number of other means. And we actually got images of the black hole that's at the center of the Milky Way, and pictures of it. Those are the standard black holes. We're talking about something very different here. Okay, we're talking about a black hole that's made of the primordial goo that came out of the Big Bang before the rest of the particles even formed. You had the primordial soup, if you like, and that stuff got gravitationally collapsed into what they call the primordial black hole. And it's different than your normal black hole that you get from a stellar collapse. I hope I answered that good enough.
Well, I guess follow up then. One would think that that if all galaxies have a black hole at their center,
yeah,
and you know better than I do what the number of all galaxies in the universe might be, and you multiply that, and you're saying that's insignificant compared to the primordial.
Well, not insignificant, certainly. It's a part of what we'd call normal mass. It's the normal mass of the Milky Way, and the normal mass of any other galaxy contains this supermassive black hole. In the cases of Milky Way, the mass of that supermassive black hole, and Connor, if I got this number wrong, feel free to fix it. It's like 1,000,000 times that of the sun. It's a big black hole. And we believe, current theory is that there's a supermassive black hole at the core of just about every galaxy. We've looked at a lot of galaxies, and we see all the evidence for the supermassive black holes. But that would be considered normal mass. That would not be considered dark mass, because that's something we can detect. We know it's there. Okay, it's visually something we can see. And when we measure the mass of a galaxy, we are counting that. We can see that. We know it's there. Okay. Dark matter and primordial black holes are something we don't see. We can't measure. They don't give off X-rays. There's no way for us to see them except through gravity effects. They don't interact with normal matter. They don't interact with light.
So to correct your number, the Sagittarius A star is about 2.3 to 2.8 million solar masses.
Okay.
So
I'm within a factor of 10.
yeah, you were close. I mean, for this purposes, it's close. You're in the neighborhood.
Couple million solar masses.
Yeah. What's a couple of solar systems would do?
Yeah.
So the other thing I would also want to add that two other theories that were popular for a very long time, but are starting to be followed by the outside because we just haven't been able to. We've tried to detect them and we've basically come up empty. Are what's now known as heavy axioms as one theory, and the other being WIMPs or weakly interacting massive particles. Those are basically a whole bunch of particle physicists going about and saying, well, we did math, we think this could work. And then they did a whole bunch of experiments to try to detect them using various exotic things like liquid xenon and have come up empty. So I was
So
still
WIMPs is out.
Yeah,
they're less
They're
favorable.
still-
They haven't ruled it out completely, but they haven't been able to give any substantial detections to it. So it's like, well, okay, what's the next thing on the list?
Yeah,
Okay.
I mean, there's probably a half a dozen different theories going around about what makes up dark matter. But like Connor said, a lot of them now have been tested and the results have come up negative for one reason or another. And so they've narrowed the list down. But there's always going to be people supporting these other theories until there's solid proof one way or the other, basically. So until they actually figure out for sure, 100% sure that dark matter is made up of this, there's always going to be people saying, well, it might be this, or it might be this, or it might be this. You just have to, all like I said, it's just right now, and it's right now. It could be something entirely different tomorrow. Today, the leading candidate is the primordial black hole. Tomorrow could be something else. The short answer, like I said, is we don't know.
One idea that's come up repeatedly and unfortunately, in my view, is MOND, which is modified Newtonian dynamics. And the problem with MOND is basically saying that gravity doesn't work over long distances the same way it works over short distances.
No, that's for dark energy.
No, that's the MOND was an alternative hypothesis to dark matter.
Oh, it was?
Yeah,
Yes.
it was for both. Yeah.
I heard it
Yeah.
as an alternative for dark energy, but not for dark matter.
The
Okay.
problem with MON is it would not produce the lensing effects that we see with dark matter. So like that image you showed of the bullet cluster was done through weak lensing, and weak lensing would not work in the same way if there would MON to actually work. So MON has been thrown out there over and over again by a fringe group of scientists. There are some who say, yeah, it kind of works for dark energy, but for dark matter, it really isn't. It doesn't hold up.
Yeah, okay. I'll buy that.
Hey, Doug, would you show the last slide again? Yeah, thanks. So, quick thought about this. Is that globe of dark matter there, is that spinning as well as the galaxy? And I'm kind of wanting to extrapolate this a little bit. If
I don't know, and there would be no way to measure that because it doesn't interact with light. So you can't take a spectrum of that stuff because it doesn't interact with light. It doesn't give off any radiation. There's no way to measure any kind of a radial velocity or anything like that. The only reason they came up with this structure, so to speak, this idea of the halo with the filamentary structure and the subhalos, is they used gravitational lensing to come up with what they think is a distribution, and they used the rotation velocity of the stars in the Milky Way disk to say, well, in order to get these type of rotation curves, they ran many computer models with different mass distributions of the halo. And they said, well, the mass has to be distributed in a certain way in order for you to get these kinds of stellar rotation curves around the galactic core. And then you have to get a certain distribution in order to meet all the criteria. There's no way to measure if the stuff is moving or not, because how are you going to do that? We can't get a spectrum of the dark matter because it's not emitting any light. So we can't see any redshift or blue shift. We can't measure any velocity. The only way we could sense that it's moving would be to study it over a long period of time and do that same kind of modeling with the rotation curves of the galaxy over. It would probably take you thousands of years to note any kind of movement in the halo structure, so I don't know whether it's moving or not.
Yeah,
So
the question of seeing it or imaging it or whatever, that was one of the questions. The other was, if you kind of extrapolate over a long period of time, you would think due to the angular momentum that eventually that would flatten out into a disk, which would maybe, kind of extend the spiral shape, I guess.
Well,
I don't know.
that's
And
an
so
interesting thought. You
well,
might expect that to happen, except how old is the Milky Way?
well,
And it hasn't happened yet, right?
right.
So,
Well,
but
so
on the other hand, I mean, consider this. If this halo of stuff, the bluish stuff there, that's 85% of the mass of the Milky Way. So it's in a nice spherical type shell, as it is now, gravitationally holding it together in this spherical type shell. The disk in the middle is insignificant. It's less than 10% of the mass. The core is the most significant part of the visible matter, but the core is sort of spherical, in shape. The
So
disk is,
I will kind of
so
equate
maybe
this.
it might not ever flatten out. It might stay in this spherical configuration for all time.
So here's my mental image of it. This is just me speculating about it to kind of answer both your questions.
Can you speak louder? I
So,
can't hear you.
hello?
I can barely hear you, Connor.
Can you hear me now?
Yeah, still
Okay.
barely.
How about now?
Still
Better or
barely.
worse? This headset.
Just go.
So to kind of hit on your points, thinking about it from an intuition standpoint, this is just, me using things that I know don't have any background here. So this is off the napkin thought, is think of this situation as the like in this image here of being the Earth. And the dark matter is basically conforming the crust, the mantle, and the outer core layers of the Earth. And that all moves, as one whole unit. It's all gravitationally bound, and it's stable because it's in a spherical shape. And then the Milky Way itself, the visible stuff that we see, is representative of the inner core of the Earth. So intuitively, I would think that dark matter is moving and rotating like the crust does of the Earth around the inner core. And the reason it doesn't flatten out is for the similar reasons. It's a stable shape because all the mass around it, although in our case, the core itself is, just pressure holding it together. So there's me being very generous here with probably a lot of things that are physically wrong. But that's how I'm thinking about how those things would behave. And it seems reasonable to me. Whether that's the actual case, I have no idea. But
If they ever figure out how to actually see dark matter, then they would be able to take measurements of radial velocities and things like that and determine if there is a motion. It wouldn't surprise me if it's rotating the same rotational rate, as the galaxy itself is rotating. That makes perfect sense to me because it is all one, stable thing. It might very well be rotating at the same speed as the galaxy itself is rotating. Don't know though.
good questions, Tom.
Yeah, it's a very good question. That'll be interesting to find out if they ever get to that point.
Okay.
The other thing I would be very interested in knowing is it contracting or expanding, or is it stable just the way it is? That would be another interesting thing to find out.
And I don't think there are any more questions or conversation topics left. So that's going to end the recording here.